For joining us today. I hope everyone's doing well and staying safe out there. My name is Victoria Getz, and I'm a Senior Business Development Coordinator at 2H Offshore. With many industry events and conferences canceled due to COVID-19, we've put together this series of live webinars to keep our valued clients and colleagues up to date on the latest happenings in the world of riser and conductor engineering. I want to welcome you all to our webinar today entitled Flex Joints, the right way to model them for SCR fatigue design. Before we get started, I'd like to cover a few important housekeeping items. Firstly, this webinar is being recorded and will be made available to you soon, so please look out for a link to that in your email. Secondly, if you have technical or content-related questions today, please feel free to ask them at any time. You can use the Q&A box that's located on the right-hand side of your screen. At the end of the presentation, we'll go through as many questions as we can, but if you have further questions, feel free to contact our speaker directly after the presentation. And with that, I'm very happy to introduce our speaker today, Guanyu Hu. Guanyu is a principal engineer at 2H in Houston. He has over 15 years of engineering and research experience in structural dynamics and finite element modeling. He's been working in the oil and gas industry for 10 years, including design and numerical analysis of riser systems. Guanyu holds a PhD degree in civil engineering from the University of Texas at Austin, and is also a PE in the state of Texas. And with that, I'm going to pass things over to Guanyu to get us started.
Thank you, Victoria, for the warm introduction. I'm excited to be here today speaking on this topic and hope you will all find the information useful. This presentation mainly covers what we think the right way to model the flex joint for SCR global fatigue analysis. As a riser designer, we have seen different modeling methods in the industry. So first, we would like to talk about and compare these methods, and then followed by evaluation discussion about what makes the result different by using different methods, and then provide a case study to show the example and give some recommendations for what should be done for riser fatigue analysis. Flex joint is a widely used riser hand-off interface for steel catenary risers, including free hanging SCR and steel lazy wave. It supports the weight of the riser from hull of the host vessel and provide articulated interface to reduce the bending moment transferred from riser to the hull structure. From riser design point of view, the most important parameter is the stiffness of the flex joint. The stiffness will be the controlling parameter for the fatigue design of the top region of the riser. And in addition to that, the fatigue load histogram from riser global fatigue analysis will be provided to the flex joint vendor so that the fatigue design of the flex joint itself will be based on the fatigue load histogram. And also the vessel porch fatigue design will also based on the fatigue load histogram provided by riser analysis. The figure at the lower right on this slide shows the interior components of the flex joint. The flex joint stiffness is mainly from the flex element on the lower part. So the flex element is made of alternating layers of elastomer and steel. When riser rotate, the elastomer elements displace in the shear plane and provide rotational stiffness. The rotational stiffness of the flex joint can be complicated and is usually a function of temperature, pressure, load frequency, and some other parameters. If we talk about the long-term fatigue, we typically use the stiffness under operational pressure and temperature condition. And the stiffness change due to temperature and pressure variations are pretty much averaged out throughout 20-30-year design life. Flex joint strength stiffness represents monotonical loading condition, while the fatigue stiffness represent cyclic cycles. So most of the time, you will likely to see a strength stiffness curve and a fatigue stiffness curve. Due to the elastomer in the flex element, based on the testing result, the stiffness curve cyclic cycles trace a hysteresis loop, which means the unloading path follows a different path of initial loading path. So the unloading path usually follows the steep initial curve. So the unloading and the reloading will form this loop shape. The two plots on the bottom of this slide show the testing results under cyclic loading. So the hysteresis behavior is very clear. You can see on this slide. Now the question is why we all have modeled it wrong. What we usually received from the flex joint vendor is this fatigue nonlinear stiffness, right line in this plot. And to apply stiffness in riser fatigue analysis, the traditional way of modeling is either directly input this nonlinear stiffness curve or apply this fixed linear stiffness at initial slope, which is very similar to what we show on the slide, this black dark line. As we mentioned earlier, the actual flex joint breakout stiffness is hysteretic, with small loading after the curve deviates from its initial nonlinear curve, as shown in this blue loop. So the unloading and the reloading path will form a good hysteresis loop around very small flex joint angle, zero flex joint angle, and never follows the initial curve. And for a large loading condition, so if you have a large loading condition, you will have a large flex joint angle. You see the same thing, that uh, this, this hysteresis loop never follows the path of the original nonlinear curve. So neither the fixed linear stiffness method or nonlinear curve method is accurate in this situation. This is because flex joint breakout stiffness is hysteretic. Objective of this study is to evaluate different stiffness modeling methods of flex joint for riser global fatigue analysis and compare and understand the impact of these methods on riser fatigue performance for different host vessels. We believe different type of vessel has different motions, so should make some difference. And at the end, we will give recommendations on the application of these modeling methods for riser fatigue, global fatigue design. In this study, we will talk about 4 flex joint modeling methods that have been used for riser fatigue design. The first one is to use a fixed linear value. The stiffness is usually taken as a fixed stiffness at small alternating angle, such as 0.1 degree, 0.2 degree. We have seen some other small numbers as well. The second method also based on linear stiffness assumption, but instead of using a fixed value for all C states, it selects stiffness based on the standard deviation of the dynamic angle for the specific C state. So a stiffness value is chosen from the nonlinear stiffness curve for each C state or each group of C state. For example, for large C state, you choose small stiffness. For small C states, you choose large stiffness. Obviously, this method is more refined than method 1. We have also seen other linearization method to obtain linear stiffness. The third and the fourth methods are both nonlinear assumption. The third method is directly input the nonlinear stiffness we just mentioned, and the fourth method is taking into account of the hysteretic effect. In this study, in the model evaluation part, the next section, the fixed stiffness method is, we think, is relative straightforward. So we will mainly focus on the method 3 and the method 4 in the model evaluation part. So in this study, we pick a still lazy wave riser under regular wave loading to evaluate the modeling method. We focus on the wave amplitude effect and the vessel offset effect. Over here, the wave amplitude effects represent loading magnitude, and the vessel offset represents the flex joint mean angle effect, because we think these are the two parameters affect the flex joint behavior the most. The flex joint nonlinear stiffness curve is provided in the plot at the lower left. This is actually a typical flex joint nonlinear curve we receive from flex joint vendor is a relationship between the rotational moment versus flex joint angle. First, we want to look at wave amplitude effect. So in this case, we assume there's no vessel offset, which means flex joint mean angle is equal to 0. The output results we plot on the slide is the bending moment versus flex joint angle. When wave height equal to 6 meter, in this case, we see that the load cycles for the nonlinear curve method always follow the blue lines, uh, which is the same as the input of the nonlinear stiffness curve on both positive and negative side. While the load cycles for the hysteretic stiffness curve um, uh, follow the hysteretic stiffness method forms this hysteresis red loop. So the red line on this slide is the result from the hysteretic stiffness method. You can see the load paths of the two methods are different. The bending moment range we find is the same. So here we're talking about the bending moment, the top minus the bottom. So the range of these two methods are the same. The bending moment range means stress cycle range and represent fatigue damage. If we increase the wave height to be 12 meters, we can observe the same thing, different load paths, but same bending moment range. We can plot the bending moment range for a series of different wave heights and can tell that the bending moment range for the two methods are all the same from this bar chart. You can see for different wave heights we select, the blue and red bar chart are always the same. So the two methods does not show difference in this case. This indicates if there is no flex joint mean angle in the system, fatigue results with different nonlinear curve method should be reasonably matched, no matter how large the load cycle is. If we plot the results of fixed linear stiffness, which is the method 1 we just mentioned, on top of the same figure, it is very clear that the fixed stiffness generates highest bending moment range, which means it predicts highest fatigue damage. If we repeat the same practice, but this time gives a 3% water depth vessel offset, now we can see that the two curves are slightly away from zero angle, and this is mean angle due to the vessel offset. And we can see that for this small wave height, the bending moment range generated by the two methods are slightly different. However, if we increase the wave, if we increase to a large wave, the difference between the two curves tends to vanish. This can be also observed from this bar chart. You can see the difference in the bending moment range only exists in this benign waves. But remember, the long-term fatigue are mainly from those small waves, so some existing mean angle in the flex joint will make difference in the fatigue results. Next evaluation is about flex joint mean angle effect. The changing of mean angle is achieved by changing vessel offset. This time, the wave height is fixed at 3 meters. When the vessel offset is about 2% of water depth, the flex joint mean angle is approximately 0.6 degree. Here we are talking about the center of the hysteresis loop, so it's about 0.6 degree in this case. And we can see a small difference of bending moment range by these two methods. If we increase the vessel offset to be 5% of water depth, then the flex joint mean angle is 1.5 degree now. So still the center of the hysteresis loop is about 1.5 degree. And the bending moment range difference is getting larger due to the fact that the nonlinear curve has a smaller slope at larger angle. So do the same practice for a series of vessel offsets. You can see that the difference between the two methods are getting larger with large vessel offset. So on this bar chart, you can see if we increase the vessel offset, we will have a larger difference between the two methods. And the hysteretic model always predicts larger bending moment range, which means it predicts larger fatigue damage. We can expect for a vessel with a significant second-order drift motion, using nonlinear stiffness curve method can be unconservative. Next, we can implement the different modeling methods to a case study to see how much difference we can expect to see in the real world. In this case study, we pick a production SCR attached to 3 different types of host vessel with a flex joint as top connection. The 3 different host vessels are deep draft semi, SPAR, and TLP. These are all widely used host vessels for catenary risers. The key riser parameters are given in the table on the right-hand side. These are all typical production SCR design parameters. We conduct time domain random seed fatigue analysis using Orcaflex. The environmental data used in this analysis are typical data in Gulf of Mexico. There are several hundred systates in each case for each vessel, and vessel motion time traces are available for all systates for each vessel type. So we applied vessel motion time history uh, in, for this global fatigue analysis. The results are extracted at 2 fatigue hotspots, 2 feet and 10 feet from flex joint rotation center. The 2 feet location represents the starting point of flex joint extension. This is also where our riser fatigue analysis result start. And the 10 feet location represent the first weld location, because that's the transition between the flex joint extension and the regular riser pipe. Obviously, the further away from flex joint rotation center, the impact from the flex joint stiffness will be less. Let's look at the results for semi first. The 4 colors in the bar chart represent 4 methods, and the bar chart includes 2 locations as mentioned earlier. The y-axis is the fatigue damage. From this result, we can tell that, as expected, the fixed stiffness value generates the largest fatigue damage, which is the most conservative approach. The fatigue results for the other 3 methods are kind of close to each other. We know semi typically has large wave dynamic motion, but a relatively small offset or second order motion. So using a hysteretic stiffness method does not show much of difference compared to other nonlinear stiffness method. So the red, you especially see the red and blue are very close to each other. This confirms what we just learned from model evaluation. So if you have small mean angle but large loading, using different nonlinear stiffness methods should be very similar. Then let's move to a spar. Spar motion is a little different. The vessel offset is typically larger, and the wave-induced dynamic motion is smaller than semi. So we can see a more significant difference between the 2 nonlinear modeling methods. In this case, the fixed stiffness is still the most conservative case. Then for TLP, TLP has a very small first-order wave-induced dynamic motion due to the large tension in the tendons, but the offset is quite large. In this case, we can see that the hysteretic stiffness method predicts much more fatigue damage than the nonlinear stiffness method. Here we are talking about the red versus blue. So you can see there is about 2.53 times difference in terms of fatigue result, which is a lot. This is due to the mean angle effects generated by the large TLP offsets. In this case, if the fatigue analysis is based on the elastic nonlinear stiffness method, which is the blue curve on this plot, it could lead to very unconservative results. This confirms what we learned from model evaluation, that mean angle can make significant impact on fatigue results for different modeling methods. Now we can come to the conclusion and the recommendations. The traditional way of flex joint modeling method for fatigue design with catenary riser is incorrect. This is because flex joint breakout stiffness is hysteretic. Um, to use the elastic nonlinear flex joint stiffness model is unconservative and is not recommended for SCR fatigue design, especially for host vessel with high offsets and second-order drift motions. The use of small angle linear stiffness is conservative and can be used when fatigue margin is large. Here we recommend using fixed stiffness for screening and the hysteretic model for detailed fatigue analysis. That's all my presentation. Thanks for your attention.
Okay, thank you so much, Guan Yu. We've already had some great questions, so I will just get started asking those. The first question is, do you get the hysteresis loop from the vendor, or do you build it from the nonlinear stiffness they provide?
Yeah, we built the hysteresis loop based on the nonlinear stiffness curve the vendor provide. We use it as a backbone curve. So based on that, we can develop the hysteretic model. We in this case, we assume it's a classic hysteresis model, and yeah, we can either model it in the rotational stiffness of the flex joint, or you can also another simple way is you can simulate the flex joint as a short beam. So the hysteretic behavior can be modeled as the bending stiffness of this short beam.
Okay. The next question is, are there any recommendations on what we should be doing for life extension assessments?
Yeah, that's a good question. For life extension, we recommend to use the hysteretic model for fatigue analysis. Um, that way, if, for example, if the original design was based on fixed stiffness, that which means there is a large conservatism in the design. So using this new method will remove a significant level of this conservatisms. Uh, just keep in mind that for life extension, you need to make sure you get the correct flex joint stiffness because those risers may be in the water for 20, 30 years already. So you should make sure your stiffness curve is correct.
Okay. Next question. If we only have the elastic nonlinear curve available, what should we do?
Oh, this is similar as the first question, I think. So again, we could still use the nonlinear curve, but uh, we developed hysteresis model based on that. So the nonlinear curve will be a backbone curve to develop your hysteresis model. And yeah, so you can either model it as a rotational stiffness or you can model it as the bending stiffness of a beam.
Okay. Next question. Does the hysteretic model reflect the actual behavior of FJ?
Yes, in one of the slides, I think it's 4 or 5, I showed the testing results. Those are from the full scale flex joint cyclic test. So that shows the hysteresis behavior. Although the for different flex joint, the hysteretic behavior might be different, but in this for the global modeling purpose, so we tend to think here we use the classic hysteresis assumption as should be good enough for global fatigue analysis. So it should be, but again, the elastomer material in the flex element. So we are talking about the rubber type material. It's if it's under the loading back and forth, the cyclic loading, the it displays this hysteresis behavior.
Okay, the next question is, how does the elastomeric component behave with time? Do wear and tear take place? And how does that influence the rotational stiffness and thus the fatigue life?
Yeah, that's another parameter that we for the global fatigue analysis, we don't typically account for that. As mentioned in the introduction, so the stiffness of the flex joint, there are a lot of parameters affect the stiffness of the flex joint, such as, the pressure, aging, temperature. All of this will be will be impact on the stiffness. But for the long-term design purpose, that those variations and the aging stuff, those will be uh, rolled into the long-term fatigue analysis. So basically, you will have some some tolerance here and there. You will have some variations here and there, but over the 20 years, 30 years, you don't see that much impact. Typically, when we receive the flex joint stiffness from the vendor, we will ask them uh, if this is for long term or if this is for short term. And when they develop these curves, I think they already take into this account of the aging or the other parameters variations. So it's pretty much an averaged stiffness uh, over the years.
Okay. The next question is, how long would it take to reevaluate a riser using the hysteretic method?
Yeah, that's that's a good question. It won't be longer than typical riser fatigue analysis. The modeling is straightforward, as I mentioned. It's respond to a few questions. The modeling is not complicated, and the simulation time is slightly longer than the simplified modeling methods. It's longer than the fixed stiffness method. It's probably comparable to the nonlinear stiffness method. So uh, I think it's not a problem considering current computational capacity and powerful software we have right now. So uh, it won't be longer than the typical riser fatigue analysis.
Okay, the next question is, are there any plans to incorporate these learnings into future industry standards such as API or DNV?
Actually, that's a good idea. It's not something we had discussed up to now. We hope to raise awareness through this webinar and our OME paper on the subject, and hopefully, industry will start to pick this up.
Okay, another question. Is there any significant difference between the hysteretic simulation models offered by Orcaflex and Flexcom?
Um, Based on our experience, there is not significant difference. I think the convergence probably is a little bit different. Uh, One of the software maybe is is more user friendly than the other, um, but in terms of application and the simulation, I think they are the same thing. It's pretty yeah, it's pretty straightforward software to use. Yes.
Okay, well, I think that was all our questions for now. And thank you so much, Guan Yu, for the information on the topic. Um, at this point, we will wrap up. But as I mentioned earlier, if you have more questions or you'd like to continue the discussion, please contact Guan Yu directly using the details provided here. I want to thank our audience for your time and participation, and we hope you all found this useful and will join us for more webinars in this series that will be happening every 2 weeks during our time at home. Check out the 2H website for more details and to sign up. And again, please look out for the recording of the webinar in your email in the next 24 hours, which will include the slide pack, and we hope you enjoy the rest of your day. And thank you.
Thank you.